So let's work the 1993 mechanics free response question number 2. And I like this problem because it involves exponential equations. And here is the problem. It says we've got a nice little car there, and it has a mass of m. Initially at rest at time t equals 0. It is driven to the right as shown above along a straight horizontal road with the engine causing a constant force of F naught to be applied. Moving the car encounters a resistance force equal to negative kV, where V is the velocity of the car and K is a positive constant. The dot below represents the center of mass of the car. On this figure, draw and label vectors to represent all the forces acting in the car as it moves with a velocity V to the right. Okay, so it's moving to the right. So we'll put it on the dot. So this is 2A. Oh, that's right, I'm off screen here. Let me zoom out a little bit. So you can draw it as a dot. I like to draw free body diagrams on a little picture of the actual object, but we do use the particle model where we pretend that the object is all located in one place. And obviously this car, gravity is pulling it down. So now it asks you to label it. So I'll put F sub G, or gravity. And you've got a normal force that's going to cancel that out. Now we use the letter N for normal force. If you put F sub N, they're going to give it to you. Don't worry about it. Normal force. And then we've got F naught. And that's a constant. Okay, and that's just the force that they gave you. And then you have this resistance force in this direction here. And this force is equal to K times V. Now, you can put the negative there, I suppose, but the negative is implied in the direction of the arrow. And so that's the free body diagram that they want you to draw. Okay, so for part B, determine the horizontal acceleration of the car in terms of K, V, F sub 0, and M. Okay, so we want the acceleration. So we're going to sum the forces in the x direction equals ma in the x direction. And, this car is only going to accelerate in the x direction. So when I have the forces here, I'm going to have F naught minus kV equals ma. And so now I just solve for A. So A is equal to F naught minus kV over m. And I believe those are the variables they wanted, the acceleration in terms of K, V, F sub 0, and m. Okay. Now, this is pretty straightforward stuff right here, right? And drawing a free body diagram, showing the forces, and then applying Newton's second law, basic stuff. They would be confused because there's no numbers in it, but this is something that regular physics students should be able to do. So if you're missing this, what that means is that you really need to go back and study that fundamental stuff of chapter 5. Okay. Now we're going to get to some stuff that's a little bit more sophisticated. Part C. Derive the equation expressing the velocity of the car as a function of time, t, in terms of K, F naught, and M. So, so we want an expression up for the velocity of the car as a function of time and all the other constants that are given. Well, for part C, well, this is the acceleration of the car. And we know the acceleration is dv dt. And so this is going to be equal to F naught minus kV over m. Now, look at this. This is really profound stuff that we're looking at right here. We've got the derivative of velocity and velocity in the same function. When you see that, you need the little red flag should go up and say, hey, I'm probably dealing with an exponential situation here. Okay? This is a differential equation, and the solution to it is going to turn out to be an exponential function. When you have the variable and its first derivative in the same expression, that's a clue, hey, I'm probably dealing with an exponential function here. All right. Now, just an aside, remember when we were talking about simple harmonic motion, we had the function and its second derivative in the expression. So that gave us simple harmonic motion. But here we have a variable and its first derivative. Okay? So there's little patterns you're going to see. So what we need to do is we need to get, I'm going to just separate the variables a little bit here. I'm going to say dv over f naught minus kv equals 1 over m times dt. Now, let's see. I don't have the solution. I forgot to get the solution manual out. Is this where they stopped? I mean, this is an expression for velocity in terms of time.
No.
They went ahead and evaluated it. Oh, v equals? Okay. So let's go ahead and do that. We're going to integrate this. And we're going to start at time 0 and go to time t. Now, when time t equals 0, it said in the problem that the car started from rest. So that means at time t equals 0, the velocity is 0. And we're going to go to some final time v. Well, let's see. I think we might have to use a little U-Substitution. Is that what you guys call it? I'm going to say I'm going to let U equal f naught minus kv. Am I still on screen? Yes. And so what I'm going to do is I'm going to say du is equal to, well, the differential of f naught is 0, right, because it's a constant. So this is going to be minus k dv. So dv is equal to negative du over k. So I'm going to substitute this in here and this in here. I'm going to substitute that in there. So let me go ahead and do that. So I'm going to have the integral of dv, which is negative du over k times 1 over u equals the integral of 1 over m dt. Now I'm going to take this and I'm going to put it on the other side. And this is du over u equals, let's see, I have to multiply by k, right, and negative 1. So this is going to be negative k over m, right? And then the integral from 0 to t of dt is just t. So I'll just get rid of that integral right now. Now, this is something that you know how to do, right? This is the natural log of u. And we're going to go from u naught to u. And now we'll do the back substitution, right? And so this is the natural log of u. Now u is f naught minus kv. And u sub 0, well, that's u when time t equals 0, right? And what's the velocity when t equals 0? It was 0, so this is just going to be over f naught. Right? Did I do that right? My calculus is probably not as sharp as some of yours because you guys, many of you do it more often than I do. This is negative k over m times t. Now, what we need to do is solve for v. Well, we're going to raise both to the power of e, which gives me f naught minus kv over f naught is equal to e to the negative k over m times t. So multiply by both sides by f naught, we get f naught kv equals f naught e to the negative k over m times t. Okay, we're going to subtract f naught from both sides. Okay, and then I'm going to divide by negative k. So there's my expression, but let's clean it up a little bit. Get rid of that negative by switching the order. So this is going to be f naught times 1 minus e to the negative k over m t. Well, let's put f naught over k out there. And I hope that's the answer, right? Is that the final expression they gave? Huh? They put a plus c on there?
No, he's fine, because basically he went through and integrated it in a different way than the equation sheet did. If you look at the equation sheet, it puts the c in front of the e, but there's no f naught in front of, on top of the k in the beginning of the expression. It's 1 over k f naught minus c, and so then when you put initial values of 0 in for t and what is it, like t and
you had your limits.
So when you add your limits, basically you get c equals f naught, so you're gonna have 1 over k. F naught minus F naught e to the negative k over m.
You know, it's interesting that they did it that way because physicists tend not to like indefinite integrals. We like definite integrals, so we try to put those limits in there, which is fine. So I'll go with this now. This is difficult. Okay. Hey, this. Right here? Yeah. Well, this is just u at the beginning, and this is just u at the end. So I just call it u naught and u. Now, what is a u naught? That's u when time t equals 0, because that was when we started. We started when t equals 0. Well, this should be from 0 to t. Now, I just didn't bother to put. I got lazy. Can't do that. Not when Seth's around. All right, so. You know, you can do that. You can put the limits in there. Yes?
You said after that, you said ln f minus kb over f. In the solution manual, it has over c.
Wait, Mr. Turn the page. Turn the page. We get your answer.
Okay. Well, here's what I by the way, I did skip a step in my head. I said, what is u naught? U naught, what is u? Like here's what u is equal to, right?
Yes.
Here's my expression for u. What is u equal to when time equals 0? Well, the car starts from rest, so v is 0, so u is equal to f naught, or u naught is equal to f naught. Right. So I just made that substitution right at the beginning. Now, look, when you do this problem, when you attempt this, many of you are not going to be able to get to this answer in the 15 minutes that they give you, right? Okay, there's test anxiety and your unfamiliarity with recognizing exponential functions and all that. It's fine, okay? They don't expect you to get 100%. But I do expect you to be able to kind of visualize what's going on here. When the car starts from rest, this force, let's look up at the free body diagram, this force is nothing. And so we get maximum acceleration. But as the car goes faster, this force grows and grows and grows and grows, which means the acceleration is less and less and less and less until we reach what's called terminal velocity, right? And when this force is equal to this force, the car will not accelerate anymore. classic situation where you get an exponential function. What I'm saying is that when we get to, if you get lost in part C, I don't blame you at all, but don't give up on the problem. When you get to part D and E, you can do it. You can still get almost all the points for D and E, even if you get stuck on part C. And this is why I really want to work this problem. This is why I wanted to work this problem with you. So let's go on to part C, or part D. It says, on the axis below, sketch a graph of the car's velocity v as a function of time t. Label important values on the vertical axis. So here's the vertical axis, all right? So here's part D. And so we've got our velocity as a function of time. Now, here's look at the free body diagram up here. Well, first of all, this is velocity and this is time. What's our initial velocity at time t equals 0? It's 0, so put a dot right there. All right. Now, here is something really cool. When it stops accelerating, that means we've reached maximum acceleration, maximum velocity, right? When it's no longer accelerating, that means it's not going to go any faster. But we can figure out what that maximum velocity is. It's not accelerating when F naught, when this force is equal to this force, we've got maximum velocity. So just solve for V. V equals F naught over K. That's going to be my maximum velocity. So what I'm going to do is just mark that velocity, just put it right there. F naught over K. Now, then I just use my intuition, my visualization of the problem. And you can say, oh, look, at first, the slope, the acceleration is at its maximum, right? So that means maximum slope. But what happens to the slope? What happens to the acceleration as time goes by? As this force grows, the acceleration becomes less and 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 less until it reaches. At 5 tau, we're going to get up here. Now, look, folks, here's what I'm saying. You didn't need to solve part C correctly to get part D right. Okay, please keep that in mind. When you're dealing with graphs, you can figure out a lot of stuff without going through all the fancy math. Now, let's take a look at the equation here. Look, if you just graph this equation, you get this, right? You just say, okay, when t is equal to 0, you get 1 minus 1 is 0. Oh. Now, when t goes to infinity, this becomes F naught over K, which is what we got right here, and it's an exponential function, so you don't know to make it a curve like this. But you didn't need to solve part C to get that. Now that's really cool. That's pretty neat that we can do that. So keep that in mind when you're doing the AP test, because remember, it's about maximizing points. All right, let's do part E. Any questions on that? This is really important. Okay, now part E. It says, on the axis below, sketch a graph of the car's acceleration A as a function of time. Label important values on the vertical acceleration. Well, on the vertical axis, I'm sorry. All right, so E. Well, let's see. One thing you could do is you could just look at this graph and say, okay, well, what's my max? This is acceleration as a function of time. What is my maximum acceleration? Well, my maximum acceleration happens at t equals 0, doesn't it? When this force is 0. Boom, that's my maximum force. So F naught is equal to ma. Okay? And so, in other words, the kV hasn't kicked in yet at t equals 0. So, I'll call that a sub 0, my acceleration at time t equals 0. So, a sub 0 is equal to F naught over m. So, I'm going to put F naught over m. Now, look, folks, take a look at this graph and just draw the slope of this graph. What's happening to the slope of this graph? Well, at first, it's maximum, and then it gradually goes to 0. Gradually goes to 0. Okay? Now, that's all you need, really. But if you really want to get crazy, you could take the derivative of this guy. Yeah. What?
Oh, do you use the acceleration for part B?
Yeah, but this is not a function of time. Well, B is a function of time way over here. Oh, yeah. Oh, yeah, you're right. Here's what I want to show you, though. My point is this, that, and this is good enough, right? Was this all the points that was offered? Okay. If you really are mathy, though, if you're a mathy, take the derivative of this.
Actually, that's what they recommend you do.
And if you do take the derivative of, yes.
Points for that.
If you say, I'm just going to do it, okay, real quick here. So if V is equal to F naught over K.
Yeah, no, they give you 2 points for differentiating the expression from velocity to make the expression for acceleration, and then you have to graph it. And you get 2 points for graphing it and 2 points for deriving it.
Yeah, so now here's what I did. I took the expression for velocity and I just distributed the F naught over K in there. So now I'm going to take this and I'm going to take the derivative of it. dv dt is equal to, well, this is 0 minus F naught over K. But then you got to take the derivative of the inside part here, which is what? Negative K over M times e to the negative K over M times t. So I zoom in a little bit. Okay, well, look what happens. The negatives go away, the k's go away, and we get an acceleration as a function of time of F naught over M times e to the negative K over M times t, which, when t is equal to 0, this is F naught over M. Ooh, just like our graph says. And then this also justifies us making a curve out of it, an exponential curve to go. I mean, what happens as t goes to infinity, a goes to 0.
Yes.
And now we even know what tau is. What is tau equal to?
L over R.
No!
RC.
Kill your people.
Hey, it means.
Oh, I'm recording this. I'm not really going to kill them.
At least remember something.
No. Hey, I want to look at the expression. Look at this expression. Tell me what tau is.
Negative K over M.
No.
No, negative M over K.
Yes.
Oh!
No, it's not negative.
Why
M
not?
over K.
Well, hey, closer.
It's M over K.
Dang it.
It's M over K. Now, okay, so you guys, we're going beyond the exam here. But
Beyond the scope of this class?
no, but we're not beyond the scope of this class.
Beyond the scope of this
Shut up.
test.
All right, now, let's take a look at units here. Because I want to. It's my class. If you don't like it, get a credential and teach your own darn class. All right. So this is kilograms. Now, what are the units for K?
Newton meter. Newton per meter. So that's
Well, you want to end up with newtons, but it's newtons per meter per second,
yes.
right? Look at this expression right here. F naught equals K times V. So if you solve for K, you get units of newtons per meter per second. So I want to show that this is going to end up being seconds. I sure hope it will end up being seconds. So, so this is going to be equal to, let me squeeze it in right here. I've got kilograms over 1 times, and then on the top here I'll just put meters per second. And then a newton, what's a newton? It's a kilogram meter per second squared. So the kilogram cancels kilograms, the meter cancels the meter, and then the 1 over seconds cancels the 1 over seconds squared. You get 1 over seconds, which is seconds. Woohoo! So if you want to go 5 tau, you got to go 5 times m over k. And then it will be 0. Or it will be added up here. So, but I mean, they could give you a problem where they want you to find the time constant, and that's how you would do it. All right. So that was a fun-filled problem. I'm really glad we took the time to do that. I'm going to be in a good mood for the rest of the day. All right.